Exoplanet research is currently going through a renaissance, as we go beyond simply detecting planets to measuring the chemical composition of their atmospheres. In the next few years, we may even be able to start to measure the properties of terrestrial planets in the habitable zones of small stars. But how do exoplanet astronomers like myself do this? How do we measure the composition of extrasolar planets? To figure this out, let's dive into the exciting world of exoplanet atmospheric retrieval. Hi everyone, Ryan MacDonald here from the University of Cambridge's Institute of Astronomy. It's exciting to think that in the space of just 25 years, we now know of over 3,500 planets orbiting other stars. We've seen gas giants orbiting far closer than Mercury, extreme rocky planets much larger than the Earth, and even a few planets residing in the habitable zone of their system. For a small subset of around 50 of these exoplanets, we have even been able to observe molecules in the atmospheres of these distant worlds. Most attempts to characterize the atmospheres of exoplanets to date rely on something called the transit method. Here's the idea. When a planet passes in front of its parent star from our perspective, a fraction of the light from that star is obscured. Larger planets block out more of the light, and so you can use this method to measure the size of an exoplanet. This is what the Kepler Space Telescope, which has discovered thousands of exoplanets since 2009, has been doing. The secret to probing the atmosphere of these planets, though, is to recognise that the size of the planet actually changes ever so slightly depending on the colour you observe it when watching a transit occur. Let's first consider a simple example where a planet has no atmosphere. It's just a ball of rock, like Mercury for instance. Then, as you see illustrated in the top right, a constant fraction of the light will be blocked. A rock doesn't care if it's red light or blue light, it will block all of the colours of light equally. And so we see a flat line showing that the amount of light blocked is a constant function of wavelength, just given on the left there by the radius of the planet divided by the radius of the star squared. But what happens if we add an atmosphere to this planet? Well, one of the things that we're most familiar with from the atmosphere of our own planet, the Earth, is that the sky is blue. This is actually due to a phenomenon called Rayleigh scattering, where short wavelength or high energy blue light preferentially bounces about or scatters around our atmosphere. And so in the case of an exoplanet atmosphere, that means the light is scattered out of the beam, and so we don't see as much blue light. So the amount of light blocked appears to slope upwards in blue light, which we call the Rayleigh slope. What happens if the atmosphere actually has atoms or molecules in it? Well, one particular atom, the alkali metal sodium, has a strong absorption feature at 590 nanometers in yellow light. And so what that means is that if you observe the planet in yellow light, the atmosphere is actually opaque, and so the planet appears slightly larger, as you see on the left there, by the transit depth increasing. And similarly, if the atmosphere has potassium, then we see the planet becoming larger again in red light, around 770 nanometers. And these two wavelengths, 590 nanometers and 770 nanometers, simply correspond to atomic transitions in sodium and potassium atoms, meaning that the atoms absorb very strongly at those particular wavelengths. So already we're getting a handle on what an exoplanet transmission spectrum looks like in visible wavelengths. But if we want to get a handle on what molecules are present in the atmosphere, then we have to go out to longer wavelengths, out into the infrared. And when we do this, we start to see very prominent absorption features due to molecules such as water. So what we expect to see if we can observe a planet passing in front of a star at these wavelengths is the planet should become larger if there is water in the atmosphere. And indeed this is exactly what we see using an instrument called the Wide Field Camera 3 aboard the Hubble Space Telescope. Transmission spectra, like what we've just talked about, are probing one particular region of the planet's atmosphere. Because if you look at this diagram, you see that the light from a star is actually passing through the boundary between the day and the night side of the planet, because most of these planets will be tidally locked. The side that is facing us in this diagram is actually the night side, and the side on the other side of the planet, which is facing the star, is the permanent day side. So the light is passing through the day-night boundary. If you observe the planet just before the secondary eclipse, when it's just about to pass behind the star, then you can actually get spectra from the day side of the planet, for instance. I won't be focusing on that here, I'll leave that to a future video. You can also observe reflected light from far out planets, like you see in this photograph here, which is a real image taken of a planet in a wide orbit around a nearby star. So you can see light which is reflected off the planet, and from that you can also obtain a spectrum of the planet, which is one way we might be able to characterise the atmosphere of Proxima Centauri b, for example. So now that you hopefully have some intuition for what transmission spectra actually look like, I want to go into a little bit more detail about how we actually produce theoretical transmission spectra to compare to observations. When light rays pass through the atmosphere, they encounter atoms and molecules along the way that can either absorb or scatter the incident light. So to build this into our models, we need a way to describe how strongly different chemical species absorb light at different colours or wavelengths. The key quantity we need to consider to understand how molecules absorb light is something called the cross-section. This tells you basically the effective size of a molecule as a function of wavelength. So what is happening here is I'm illustrating this cross-section for the case of water in vapour form. And notice how there are a number of peaks. It looks like the water molecule seems to appear larger at about 1.15 micrometers and at 1.4 micrometers. So what's happening here is that at these two particular wavelengths, excitations, vibrational motions of the water molecule can be excited by incident light. And so this means that water absorbs very strongly at those wavelengths. And you'll also notice that there's lots of fine substructure going on here. Lots of jaggedy transitions. That's actually caused by rotational motion of the water molecule. These quantities are computed by solving from first principles the Schrödinger equation of quantum mechanics for a particular molecule, which is an incredibly complicated and involved calculation. In practice though, we don't have observations of exoplanet atmospheres, usually at least, for anywhere near this resolution. Here for clarity, I'm showing what the water cross-section looks like if you apply a Gaussian to smooth it. What I want to show you now is a comparison of how different molecules that can be present in an exoplanet atmosphere absorb, so we can get some intuition for which molecules absorb at which wavelengths. So for instance, let's add methane. We see that methane in this particular wavelength range, which can be observed by the Wide Field Camera 3 on the Hubble Space Telescope, we see that methane has overlapping absorption features at around 1.2 and 1.4 micrometers, but methane has a strong absorption feature at about 1.7 micrometers. And so if we were to see an increase in the absorption of a planet at 1.7 micrometers, that could potentially serve as a detection for methane in the atmosphere. We can also consider nitrogen-bearing species like ammonia that you see here, which has a strong absorption feature at 1.5 micrometers, and similarly, hydrogen cyanide also has an absorption feature at about 1.55 micrometers, which overlaps slightly with the ammonia. Now, all of these cross-sections that I've shown you have been evaluated at a specific temperature, at about 900 degrees Celsius or 1200 Kelvin. Now, as we change the temperature of the planet, then we gradually see that the shapes of these absorption features change. And so this means that from the shape of absorption features, we can actually extract the temperature of the planet's atmosphere. Why is the temperature so important? Well, if you've ever climbed a mountain, then you'll know that the temperature of the Earth's atmosphere is not constant with altitude. In fact, it decreases with altitude in the lower atmosphere, increases briefly once you hit the ozone layer due to absorption of UV radiation, and then increases once more once you reach the edge of space due to X-rays and other high-energy radiation. Now, in the specific case of transiting exoplanets, light rays actually pass through a number of layers in the atmosphere, thus sampling a number of different temperatures and pressures. With all of these ingredients, once you have specified the chemistry, temperature structure, and cloud or haze properties of the atmosphere, you can calculate a transmission spectrum. This basically involves working out the overall amount that each ray of starlight is absorbed, then summing over all of the rays that pass through the atmosphere at the day-night boundary. It boils down at the end of the day to numerically solving a set of equations via a computer code. I'll spare you the laborious technical details and simply show you the results of such a calculation. So just like we did with the qualitative example earlier, let's start and look at a planet that has no atmosphere, for which we expect the fraction of the light from the star that is blocked by the planet, the transit depth on the left-hand side, to just be a flat line, given by the radius of the planet divided by the radius of the star squared, here 1.46%. for a typical hot Jupiter. Now let's add an atmosphere composed of hydrogen and helium. And again, we see this Rayleigh slope going up towards blue wavelengths. We can then add the alkali metals, sodium and potassium, and we see those sharp absorption features. And in the infrared, we can add water. So with all of this together, this is the kind of transmission spectrum we expect to see as an output from a radiative transfer code which I went away and wrote. So now let's add a few more molecules to see how this changes the spectrum. We can add methane, which then produces an extra absorption feature at 1.7 micrometers. We can also add ammonia, and notice that it adds a kind of slope that appears at about 1.5 micrometers. And just to remind you, I've highlighted the particular range that we can get high precision measurements right now using the Hubble Space Telescope. We can observe a little bit at other wavelengths, like we can observe the alkali metals, for instance, using other instruments, either on the ground or using an instrument called STIS on the Hubble Space Telescope. But the best observations at the moment come in that wavelength range, 1.1 to 1.7 micrometers. So this is the model that we have altogether. But to this point, we haven't considered what clouds do to the exoplanet transmission spectrum. So this is actually a cloud-free atmospheric model. If we add a cloud deck, it's almost like raising the opaque surface of the planet. A continuum rises up that cuts off the bottom of the absorption features. And so this means that if we have a very high altitude cloud deck, you basically just get a flat, boring spectrum with no information and absorption features in it. You can also have a haze, which can scatter light, and that causes the slope, the Rayleigh slope, to actually become stronger. And so you see this slope curves upwards and becomes slightly steeper overall. In the early days of exoplanet atmosphere research, this is pretty much where people would stop. They would generate a few transmission spectra, often choosing which molecules to put in by hand, until they found one that fit the observations. For example, here is a transmission spectrum that was published in 2008, where the observations here are given by the triangles, and you notice that a model which only includes water given by the blue curve there does not match the observations longer than about 2.1 micrometers. However, the model which includes methane, the orange curve here, does match those observations. So this was used to claim the presence of methane in the atmosphere just by comparing a few models almost by eye. The problem with this approach, called forward modelling, is that you don't know whether the solution that you found is the only possibility. Indeed, there could be a wide range of atmospheres that can still match the observations. So to address this issue, you need to use something called an atmospheric retrieval algorithm. Instead of starting with an assumption of what a planet's atmosphere is made of, a retrieval algorithm starts with the observations, for instance, observations from the Hubble Space Telescope, and tries to work backwards to extract the underlying chemical composition, temperature structure, and cloud and haze properties of a planet's atmosphere, which is something we call an inversion technique. It works backwards from the data. So how does a retrieval algorithm work? If you look on the left-hand side, then what we have is a schematic just showing a model that is doing a reasonable job of fitting some observations. And this model might have a particular temperature and a particular amount of water in the atmosphere. And so, as you can see from the left, it's a pretty good model. It seems to go through most of the data points. But what will happen if we increase the temperature in this model whilst fixing the amount of water? Then what happens is the planet's atmosphere expands as you heat it up, and that results in larger amplitude absorption features. And you now see it doesn't do that good a job at fitting the observations. So the model isn't that good. Similarly, if you increase the amount of water, but hold the temperature constant, then with additional water you expect the atmosphere will absorb more at the wavelengths where water absorption is prominent. And again, you don't get that good a fit. So the idea is, if you can generate millions or hundreds of millions of different models, then you can map out the parameter space, which typically will be way, way, way higher than just this two-dimensional example here. You could have 10 or 20 dimensions. But once you've generated all of these millions of models, you can then produce something called confidence intervals or contours, where you identify the regions of the parameter space that are consistent with the observations. And once you've found them, then you can do something really clever. Here's the idea. In this simple example where we're just considering an atmosphere at a constant temperature and just with water in the atmosphere, what we can then do is if we draw vertical lines down, we're basically counting how many models there are at a given value of the water for all possible values of the temperature. Because the statistical algorithms that we use tend to cluster around the regions that fit the observations. And so there'll be many more models closer to the actual value of the water that the planet has. And so what we see is, when we plot a histogram like this, is we get a peak centered on the true value of the water of the planet. We can do the same for the temperature by drawing horizontal lines and counting all of the models for all the different values of the water at each value of the temperature in a given bin. Then we can produce a probability plot, shown by a histogram here, for the temperature of the planet. Usually though, we invert the labels, flip them around, and show it like this. So in this particular example, what we've done here is something called marginalization, where we have summed over the values of all of the other parameters in a model, and this enables us to constrain from the observations the underlying planetary parameters, here the temperature and the amount of water in the atmosphere. And from looking at the histograms, basically starting in the centre and working your way outwards until you have enclosed 68% of the probability distribution, something we call the 1 sigma level, you can then produce constraints, which are given by the little plus and minus values at the top and the bottom there. So here you see, for instance, if you look at the temperature, the centre value, or in this case the median of this probability histogram, is centred at 600 Kelvin, and then the width in the positive and negative direction is 120 or minus 175 Kelvin. So by doing this, we have been able to extract constraints on the temperature and the amount of water present in this atmosphere. Here is a quick diagram showing what a real atmospheric retrieval outputs, and you see it is a lot more messy. In this particular case, there is something like 14 parameters, but the basic idea is the same. Produce many, many millions of models, and from the exploration of the parameter space, we can extract the underlying properties of the planet's atmosphere. Now that we've explored the basic ideas behind exoplanet atmosphere retrieval, I want to talk about a specific retrieval algorithm that I have been developing. One of the specific problems that I've been trying to address is illustrated here, where you see that two different transmission spectra, one with a low amount of water and a cloud that's very deep in the atmosphere, and another with a high amount of water and a cloud which is quite high in the atmosphere, can produce very similar transmission spectra, which is something we call a degeneracy. And the problem is that if the spectra just look exactly the same, then how are you supposed to measure the amount of water present in the atmosphere? But last year I found something very interesting. It turns out that this degeneracy only actually manifests if you assume clouds obscure the entire terminator. If indeed you allow the terminator to have both cloudy and non-cloudy regions, as shown here in this exaggerated diagram, then you can essentially peer through the clouds and measure the chemistry of the planet. It was this realization that the degeneracy between clouds and chemistry can be resolved by considering two-dimensional clouds that features at the heart of my code, Poseidon. Earlier this year, I submitted a paper, now published in Monthly Notices of the Royal Astronomical Society, that outlined how the Poseidon algorithm works. In this paper, I applied Poseidon to the highest quality transmission spectrum available at the time, that of the hot Jupiter HD 209458b, and found some really exciting results. So let's dive straight into them. If we focus in on the infrared observations taken by the Hubble Space Telescope's Wide Field Camera 3, then we see something very interesting. We see signs of a large water absorption feature at 1.4 microns, as we discussed earlier, and a little bump at about 1.2 due to water as well. But the interesting thing is that there seems to be this extra slope at about 1.55 micrometers, which I actually mentioned earlier could be produced by ammonia in the atmosphere. So from generating 100 million models, exploring all of the possible explanations for this transmission spectrum, my code concluded that you have to put in either ammonia or potentially hydrogen cyanide in order to match those data points that are at a longer wavelength than 1.5 microns. And this was incredibly exciting because there hasn't actually been any definitive evidence of any molecule containing nitrogen in an exoplanet atmosphere to date. And actually, by computing the significance of this detection, we estimated it at least 3.7 sigma, meaning that this is a reasonably high confidence detection of nitrogen chemistry in an exoplanet atmosphere. Now, I should stress at this point that these observations are not precise enough for us to tell whether it is ammonia or hydrogen cyanide which is causing this additional absorption, but we're reasonably confident that one of these two nitrogen-bearing species is responsible. We were also able to extract the pressure-temperature profile, or the temperature structure of the planet, from the observations. And you notice that this planet is quite hot. The temperature is around 1400 Kelvin, or 1100 degrees Celsius, and generally speaking, as you go deeper in the atmosphere at the day-night boundary, it gets hotter and hotter and hotter as you go down. We were also able to extract some pretty interesting constraints on how much of each molecule there is in the atmosphere. And one thing that I really want to draw your attention to here, the colours incidentally are just showing what happens if you assume different cloud distributions on the planet. In all of these cases though, the water on this planet appears to be significantly drier than what you would expect if the planet was just made from the same quantity of each element that you see in the sun, for instance. So this seems to be a particularly dry planet, and that could have implications for how it formed. And you also notice that we can see a quite sharp peak for ammonia in the case of a cloud-free model, and then slightly broader distributions for models that have partial clouds or uniform clouds. And we also get a constraint potentially on the amount of sodium in the atmosphere as well. So what does all of this mean? Well, if future observations are able to confirm the nitrogen chemistry detection, then we could be on to an entirely new window into exoplanet atmospheres and how planets form. In particular, the nitrogen chemistry that we're seeing shouldn't exist if the atmosphere is in chemical equilibrium. So what this effectively means is that there must be some kind of disequilibrium process causing this nitrogen to be dredged up or created in the upper atmosphere. Two potential ways that you could cause this is there could be large vertical mixing of columns of air dredging up ammonia or hydrogen cyanide from the deep atmosphere. Or potentially what you could have is you could actually have photochemical reactions in the upper atmosphere, basically interactions between UV light and chemicals like methane in the upper atmosphere, producing hydrogen cyanide, for instance. So where do we go from here? Well, Poseidon is still under active development and becoming more capable over time. We have to remember though that we're only 2 years away from the first transmission spectra observations with the James Webb Space Telescope, so it's vital that we have the tools that can retrieve the properties underlying these spectra ready to go. Recall that actually most of what we've learnt about exoplanet atmospheres to date has been accomplished using low-resolution instruments that were not designed to do this. But all of this will start to change in the years to come. And just imagine what we will learn about the incredible diversity of alien worlds out there, just waiting to be explored. Last time, I spoke about the progress SpaceX is making towards the first Falcon Heavy launch later this year, which led to a varied array of responses. I particularly liked Tebusky 78's analogy, with ongoing efforts to develop fusion power, given that the Falcon Heavy has been 6 months away since 2013. I'm actually quite optimistic this time around though, similar to Ludwig, especially given that Elon recently confirmed that the launch remains on track for October. I'll be back a little over 2 weeks from now with the latest updates on human Mars missions, but in the meantime, please let me know if you have any questions on exoplanet atmospheres or other topics down below. And don't forget to subscribe to keep up to date.